Hello and welcome to the third and final video on the Intro to R and RStudio. In this video, we're going to talk about how to create a scatter plot for two continuous variables, run a correlation, run a simple or nearly squares regression, run a multiple or less regression, assess multicollinearity, and run a commonality analysis to determine amounts of shared and unique variance in the regression, export the results out of RStudio into your local machine, such as like a CSV file. We're also going to show you how to export the APA formatted regression tables and descriptives out of Word, or out into a Word document. So we're back in R, and we're going to answer questions about the relationship between two continuous variables. So linking back to our scenario. Here we're trying to determine if the relationship between GDPPC and corruption, leaving corruption on its original scale from 0 to 10. The most basic graph to do this for two continuous variables is a scatter plot. The scatter plot will show us that the two variables appear to be related. We're going to follow up this visual inspection with two tests. First, a correlation to determine how tight the relationship is between the two variables. So a correlation close to 0 indicates that there's no relationship. A correlation close to 1 or -1 indicates a relationship that's very close to a perfect line, and whether or not that relationship is statistically significantly different than the null of relationship of 0. Second, the regression is going to tell us the nature of that line in question. A line is defined by a slope and an intercept, and the regression output will tell us if either of those is statistically significantly different than 0. So first we're going to do is we're going to create a scatter plot. So we're going to plot our y-axis followed by our x-axis. We're adding a title using the main equals command, labeling our y-axis, labeling our x-axis. So I'm going to go ahead and run that. So here is our visual. Now imagine a line that tries to minimizes the distance or the residual between the point and our regression line. We can actually do that by using the abline function. Now LM is actually running a linear model. GDPPC regressed on corruption 2. That line is going to be red, and then we go ahead and add that in there. That's superimposing that line of best fit. Now if we run a correlation using the core function of our two variables, we're using complete observations. The method is going to be Pearson because these are two continuous variables. That gives us a negative 0.89 correlation, so it's a strong negative correlation. Is this statistically significantly different than 0 though? To do that, we need to use a different function. We're going to use core test, which can only be used one variable at a time. We use that same code we used before. When we do that, we have our Pearson's product moment correlation. Our T statistic degrees of freedom, it is statistically significant. So we're going to reject the null in favor of the alternative. We have our 95% confidence interval, our lower and upper bound, and there's our estimate we had before. So that looks great. Now what I'm going to do is we're going to use the regression, which gives us additional information about the relationship of the two variables. It allows us to predict the value of one variable given the information of another. We're going to regress GDPPC, our dependent variable, over corrupt2, our independent variable. The first thing we need to do is we need to specify the model. So LM means it's going to be a linear model. We have our outcome variable, then tilde, independent variable. We're saying take GDPPC and regress it on this variable. It's going to run that, and now we're going to store the results as an object called model1. When we do that, we have a new object called model1. If we expand it, we have coefficients, residuals, effects, and some other information in there. If you want to see the results, we're going to type in summary parentheses the regression object, or the output object. When we do that, let's go ahead and expand this a little bit. We have our regression equation, our residuals minimum, median, and maximum, our coefficients. So knowing nothing about a country's corruption score, what's our best predicted guess? Our best prediction is about 40,000, and that intercept is statistically significant, the p less than 0.001. And for each unit increase in corruption, there's a 4,761 point decrease in GDPPC. So that's our rise over run. For each unit increase in corruption, we're seeing a reduction in how well that country's economy is doing. Now we have our degrees of freedom. So our F statistic on 1 in 49 degrees of freedom. Our p-value omnibus regression ANOVA is statistically significant, less than 0.001. And based on this, we're able to account for roughly 80% of the variability of GDPPC by using corruption too. When we include additional predictors, we'd want to interpret adjusted R squared, which gives us a little bit less bias from having so many predictors in our model. This equation can be written out as our predicted GDPPC equals our intercept plus negative 4,762 times corruption 2 plus some error. If you wanted to add additional variables, let me go ahead and put it back to the same size. We can simply add in a plus between the variables. We're going to go ahead and run this as a multiple linear regression. Storing that as model 2, running a model, similar information. Our intercept is a little bit lower for our best guess. Each unit increase in corruption 2 is still a significant amount, but not as large as before, and these are all statistically significant. And here we did OECD membership, so we actually used a factor here. So if they are a member, so yes, compared to the reference, which is no, there was an 8,153 point increase. If they were not a member, this is going to drop out of the equation because it's 8,153 times 0, essentially. With this, we were able to account for almost 84% of the variability. We use our just R squared, it's about the same. And this is overall statistical test is statistically significant for this omnibus ANOVA. Now what we can also do is we can then also run things like some regression diagnostics. So we're using a par 2x2, so it's going to create a 2x2 figure. We're going to plot model 2. That's going to be residuals versus fitted scores, or normal QQ. So looking at this, we have a couple potential outliers, and we see them again here and here. So actually we might want to isolate those cases and run the regression both with and without them. We can also use VIF. So VIF looks at multicollinearity. Now VIF is the inverse of tolerance. So VIF is variance inflation factor. These aren't too high, but let's say that there's still a level of multicollinearity. So if we imagined a Venn diagram of, let's pretend that this box is our outcome variable. We're taking slices of that by each variable. Sometimes there's overlap in what's accounted for, because this variance accounted for. That overlap is where we can actually look at commonality. So it might be that one overlap is subsuming that plus the other. Yeah, let me go ahead and draw this out a little bit. So imagine this is GDPPC. Here is corruption 2. If we have OECD membership, there's no multicollinearity, there's no shared variance. But let's say OECD membership could account for that. It could still be an important amount or theoretically important, but there's nothing new. It's already accounted for by corruption 2. So rather than having to remove variables, what you could also do is what's called run a commonality analysis. For more information, I'd recommend the article by Crehe et al. 2012 in Frontiers of Psychology. Let's get rid of that. So what I do is we're going to actually use commonality coefficients. And that tells us each coefficient, what is the unique portion of variability accounted for by corruption 2. Of the 84%, it's almost 30% of that. Unique to OECD, it's about 5% of that 84%. And common, that's the overlap. There's about 65% overlap that's accounted for by both of these together. So this is another way of looking at commonality. There's also things like reg R, and if we do model 2, Reg-R is a function from the y-hat package, which is where we got commonality coefficients. This tells us a whole bunch of other information. This tells us our standardized coefficients. So for each standard deviation increase in corruption, there is a negative 0.69 standard deviation decrease in GDPPC. We have our structure coefficients. Square these, and it's how much each variable could have accounted for, controlling all of the variables within the model. Here's our commonality analysis, as well as different types of effect sizes. So what we're going to do now is we're going to go ahead and show how to export results out of R and into a CSV file. So what we can do is, let's say one of the coefficients for our regression, so intercept in our two slopes, or our coefficient for corruption 2 and our coefficient for OECD member, we're going to say, okay, we want to get the summary, specifically the coefficients from that model. We're keeping it as a data frame and then writing it out as something called model2.csv. I'm going to go ahead and minimize this. I'm going to move this over here. And now in Excel, we have our coefficients, our labels, our estimates, our standard errors, our t, and our statistical significance test with those. Going back to R, we can also do this with any sort of variable we want. Like let's say we wanted that OECD corruption table we made before. If I do that, I'm going to minimize R. Here's our other table. Open it up. Here's our table we made before too. And then this is a really nice feature. So I'm going to use the APA tables package we opened up before. I'm going to use the function APA core table. That's going to give us means standard deviations for all the variables in our CS data frame. I'm going to store this as something called descriptives.doc. I'm going to label this as table 1. I'm going to have it show the constant intervals, and it's going to be in landscape format. I'm going to go ahead and run this. I'm going to print a version of it out in the console. I'm going to minimize this. I'll move this file on my desktop over here, and I'm going to go ahead and open it up. So it went ahead and it created a formatted table. Now you probably have to move the margins over a little bit to fit everything in. But that's our correlation table with our mean standard deviations and all our specific variables of interest. All the variables here have to be numeric though. We can also take our regression model and export that. So I'm going to use the APA reg table. I'm going to have it export model 2. We're giving it a name. We're going to call this table number 2. So if I run this, let me minimize R for a second. I'm going to open it up. Here's our regression table. It has our predictors, our unstandardized coefficients, the constant intervals around those, our squared semi-partial correlation, which is the amount of unique variance accounted for. Confidence intervals around that are R squared, and our R squared 95% CI around that too. And the nice thing is we have everything already in this code. If I was to clear all of this and just highlight all of this and rerun it, it will run really quickly. So we can go ahead and close all of this out. And this is R. Again, if you have any questions, it's always good to go through the documentations. Like let's say you want to learn about using linear mixed effects or multi-level modeling. You can open up the help package, and let's say I wanted to learn how to use the LMER function. So I can figure out how the usage of that function, what each part of it is and what it's expecting, the details, and then I can actually take these examples and copy them and paste them into here and run all of them as well. I hope this was helpful. Again, there's tons of resources out there to learn R. I highly recommend it, and it will always be free. Thank you so much for watching.